today's lecture will be a central limit theorem. So, for n bigger than or equal to 1, let us say we have random variables x1, x2, xn. Let us assume they are all from the same sample x. So, they are both independent and identity distributed from a distribution x. And let us assume x has two characteristics. One is that the mean of x, let us call that as mu, is finite, and the variance of x, let us call that as sigma squared, that also is finite. Okay. Now, suppose I look at the sample mean. So, x bar, which is just x1 plus x2 plus xn divided by n. We have seen this before, that the two things we have seen about x bar. One is that the mean of x bar is same as the mean of x1 plus x2 plus xn by n. By linearity, all of them have the same mu, so it will just be mu. And we also seen that the variance or the standard deviation of x bar, that is going to be equal to sigma by root n. Right. So, that means suppose mu was here somewhere in space, mu was somewhere here, means all this is saying is that x bar, you are likely to find x bar in a smaller and smaller window as n gets larger. So, that means like this minus sigma by root n plus sigma by root n, and this interval shrinks as n goes to infinity, and x bar is going to concentrate around mu with high probability. Right. So, x bar is concentrating around mu with high probability. Very nice. So, this we have seen before as xn bar goes to mu in probability or with probability 1, the weak law of large numbers or strong law of large numbers. So, this is like, I will write this down, it's like the weak law of large numbers. So, today what I want to do is I want to understand how does the standardized mean behave. So, I standardize the mean. So, in the sense that I look at, so let us standardize. So, I look at yn bar, right, yn, which is just I subtract the mean of x bar, which is mu. So, mean is 0, and I make it standard deviation 1. So, I divide by sigma by root n. Right. So, that is going to be equal to root n times x bar minus mu by sigma. Right. Now, given this, now we know that yn has mean 0 and variance 1. Right. So, standardize. So, E of yn is 0 and the variance of yn is 1. So, typically, since I have taken a very general x, x1, x2, xn, it is hard to find the distribution of yn. Right. So, the question, so one factor is that it's hard to find, hard to compute the precise distribution of yn. So, hard to compute probabilities concerned with yn. Even if you know the distribution of x precisely, this can be quite hard to do. But if you don't know this, also there is sort of a remarkable fact called the central limit theorem that allows you to compute the limiting probabilities in some sense, or the limit distribution in some sense. So, the key punchline is the following. The key is this sort of central limit theorem. It's a remarkable result that states the following, that one can approximate the distribution of yn by a standard normal narrowable random variable for large n. It's kind of a nice remarkable result. That is, as n gets larger and larger, one can actually show that yn approaches normal 0, 1. So here's a simple simulation exercise one can try. I'll write the exercise down. So a simple exercise one can try. So one is that we've already seen the binomial central limit theorem last time. Okay. So one could do the following. Just say let's say sample let's say x1, x2, xn data from, let's say, let's do something called Poisson lambda. So Poisson lambda has definitely finite mean and finite variance. One could compute, let's say n equal to 100, let's say 100 samples, compute x bar, right? And then you repeat this step, let's call this step. Step 2 is you repeat step 1 100 times. So repeat 100 times and plot a histogram. By it I mean plot x bar histogram. So that will give you a simple. It will try to show you that the histograms at least look like the Gaussian histogram. You can try this exercise. This is an R exercise you can try. Okay. So now I'll sort of state the general central limit theorem in its complete preciseness. So here's the theorem. Sorry. So idea is that let x1, x2 all be IID random variables. And all I require is that they have finite mean mu and finite variance sigma squared. That's the first step. In addition, let's assume for this theorem, let's assume that they also have a finite moment generating function. Then what you can say is the following. Then the probability that, or maybe before the probability, let me define. Suppose yn is equal to root n of x bar minus mu by sigma, the standardized mean, then the probability that yn is less than or equal to x, this distribution function of yn converges as n goes to infinity to the probability that the z is less than or equal to x, where z is distributed as a normal random variable with mean 0 and variance 1. So it's a very remarkable result that tells you that you have any random variables sequence, don't worry distributions, you take their average, it's going to look like normal. So most averages will look like normal. That's sort of the fundamental aspect of central limit theorem that one uses all the time in statistics and probability. So let me just make a couple of remarks about the result. I will not prove the result. The proof is outside the scope of this class. So maybe I'll give a sketch of the proof or the idea at the end of this lecture, but some remarks first. So the theorem holds more generally. The existence of moment generating function is not required. The central limit theorem holds much more generally. Sorry. Holds only with mu finite and sigma squared finite, but the proof is much more complicated in that case. The first remark. The second remark is that there's an equivalent formulation. That is, you look at xn bar, right? X bar is what? X bar is just x1 plus x2 plus xn by n. Suppose I call the numerator as Sn, so I call it Sn by n, where Sn is just the sum of the random variables. Then one can phrase the following. Suppose Zn was equal to, okay, just same as Yn, but okay, let me add the Yn. So Yn in terms of Sn, what does it look like? Yn is root n x bar minus mu by sigma. That I'll write as root of n times x bar is just Sn by n minus mu, the whole thing divided by sigma, and that's going to be equal to, if I multiply root n out, so I'll get Sn minus n mu, the whole thing divided by root n times sigma. So it means the central limit theorem tells you, implies that the probability that Sn minus n mu divided by root n sigma less than or equal to x converges as n goes to infinity to probability that z is less than or equal to x, where z is normal 0 1. Of course, now I just have to be careful here. Here I didn't say x is any real number. And here also same thing. I have x is any real number. That's first two remarks. The third remark is the following that I like to sort of state is the following, that so CLT gives you how a specific statistic, that is a sample mean, converges to normal 0 1. There are, so the above central limit theorem, let me say the above central limit theorem focuses on a specific statistic, that is x bar, that is a specific statistic. Right. But in general, it holds much more generally. That is, there are other statistics as well where central limit theorem holds. So it's remarkable as well to see that the central limit theorem also holds. The result also holds for sample median, for example. Median, and there are many other statistics that for specific random variables also converge to normal random variables. So it's like a sort of a very remarkable result in that sense. The last remark is it does not say how quick the approximation is. The result does not say how good the approximation is. The result does not specify how good the approximation is. So example, like as a practitioner, it's maybe very hard to use the result because you may have to wait for large n for this to be close to normal, right? It may not happen very, very quickly, right? So if you have distribution of the data set, you'll need to know a little bit more about the distribution to understand how quick the convergence is. Otherwise, it's sort of it doesn't give you how fast the thing goes through. So the other common characteristics: sample mean, sample median, sample proportion, and it covers a large class of x1, xn to x, and it doesn't really apply if the second movement fails. It doesn't really apply. For example, you can check one simple exercise you can check is you can try and simulate and check what happens if x is Cauchy. So you can check what happens to x bar when x1, x2, xn are IID Cauchy. Cauchy 1, let's say, because here the thing is that the second mode is infinity, so CLT should not hold. You should be able to get a clear example where CLT will not hold.